Hey everyone, welcome back. This is Maddie. In this video, we'll be learning types of asymptotic notations. This is very important topic in an algorithm because notations are used for representing the symbol form of a function or showing a class of function. In our previous videos, we have learned big O of n, right? Big O of n, big O of 1, big O of log n. That's one of the asymptotic notation. Now let us see all three types of notations. The first one is big O and the symbol is big O and it indicates the upper bound of a function. The second type is big omega and the symbol is omega. As we all know, lower bound of a function is represented using big omega. The last type is theta. We all know the symbol. This represents average bound of a function. Now let us discuss each of these notations one by one in detail. The first one is big O. As we already know, this represents the tightest useful upper bound. Let me just take the textbook definition of big O notation. The definition says the function f of n is said to be big O of g of n if and only if positive constants c and n naught such that f of n is less than or equal to c into g of n for all n greater than or equal to n naught. This is the textbook definition of big O notation. Let us understand this definition with an example. I'll consider f of n as 2n plus 3. Now, as per the definition, we need to write the big O of g of n for the f of n. As per the definition, f of n should be lesser than c into g of n for all n greater than or equal to n naught. We know f of n, that is 2n plus 3, less than or equal to something. In this place, I need to write in something such that the value of it should be greater than the left hand side f of n. Let's consider c into g of n as 10 into n, and this c into g of n can be anything, but it should always be greater than the left hand side f of n. Let us check 10 into n is greater than 2n plus 3. 2n plus 3 less than or equal to 10n. To validate that, let's consider n equals 1 and we'll substitute the value of n in this equation. 2 into 1 plus 3 less than or equal to 10 into 1. 5 is less than or equal to 10, which is true for all n greater than or equal to 1. Here f of n is 2n plus 3, c is 10, g of n is n, and all these terms holds true for big O definition. Therefore, the time complexity is big O of n. As per the definition, f of n equals big O of g of n. G of n is nothing but n. So the time complexity of 2n plus 3 is big O of n. The simple method to know this c into g of n is making the left hand side terms, that is f of n, a multiple of n and putting it on the right hand side. Let us try to do that. Here in our previous validation we have considered n as 1, right? Instead of that, we can make the left hand side terms a multiple of n and we can put it in the right hand side. Let us try to do that. We know f of n is 2n plus 3. We need to validate whether f of n is less than or equal to c into g of n. Simply what we can do is we can make left hand side terms, that is 2n plus 3, a multiple of n, that is 2n plus 3n. Here we are multiplying both the terms with n. Since the first term 2 already has n, so we are ignoring that. We are just adding n to 3. After adding them, we'll get phi n. And we know this phi n will be always greater than 2n plus 3 for all n greater than or equal to 1. And this condition holds true for big O definition. That's the simple method. Here f of n equals 2n plus 3 function belongs to the class n, and the inputs above n are upper bound and the inputs below n are lower bound, and n itself is the average bound. Let us see that with the time function comparison. We know 1 is less than log n, which is less than root n, less than n, less than n log n, less than n square, n cube goes till 2 to the power n, 3 to the power n, and this goes till n to the power n. We know the function 2n plus 3 belongs to the time function n, so the inputs above n are considered as upper bound, including the time function n, and the inputs below n are considered as lower bound, and n itself is considered as average bound. For the function 2n plus 3, even the time functions n square, n cube, or 2 raised to n can also be considered as big O. Even though n square, n cube, 2 to the power n are true, but we should always consider the closest function to the upper bound. Which is the closest function to the upper bound? N, right? So we will always consider the tightest upper bound for big O. The tightest upper bound here is nothing but the time function n. Let us understand this big O notation using real world scenario. Imagine your car's max speed is 100 km per hour. And can we say it as, is it true if we say the car speed is less than or equal to 200 km per hour? Yes, this is true. Is it true if we say the car speed is less than or equal to 1000 km per hour? Yes, even this is true. But these two statements are misleading. The correct lowest upper bound is 100 km per hour. We can also say car's max speed is less than or equal to 200 km or less than or equal to 1000 km per hour. But the correct one is 100 km per hour, which is lowest upper bound in this case. I hope big O notation is now clear. That's it for this video. In the next upcoming video, we'll be learning big omega and theta. Thank you all for watching. See you in the next one.